This is the pre-lab talk for experiment number 9 for Chem 110 lab, Thermochemistry Part 2. The goals for this lab are to use measured temperature changes to study the relationship between reaction stoichiometry and delta H, and to also study Hess's law of heat summation. We will also use our data to calculate the enthalpy change for an acid-base reaction using calorimetry calculations. For today's safety pause, we note that we are using all acids and bases for this experiment. Acids and bases have the hazard of being corrosive. Therefore, great care should be taken when handling them. If any acid or base gets on your skin, you should wash the affected area immediately with running water. For waste disposal, we note that nitric acid, as an oxidizing acid, needs to be disposed of in a special waste bottle. All other aqueous waste can be flushed down the drain after neutralization with plenty of running water. And as always, we want to remember to goggle it and wear your flame-resistant lab coat. In this experiment, you'll be running multiple acid-base reactions and measuring the temperature change that occurs when those reactions take place. Why are we measuring the temperature change, and how is that going to help us to make some comparisons that deal with enthalpy changes? Let's note a few things. We know from lecture that the enthalpy change, delta H, is related to the heat evolution at constant pressure. We also know from calorimetry that Q can be calculated if you know the mass, M, specific heat, lowercase c, and temperature change, delta T, for the system. We note that delta H is directly proportional to delta T in our equation. Therefore, we can make a direct comparison between the delta T that occurs for a system and the delta H for the system. This is what we hope to do in this experiment. Relate delta T and delta H for several different reactions. We'll change certain things about the reactions, such as the stoichiometry, which will be changed by changing the concentration of our reagents, and whether or not our reagents are strong or weak acids or bases. Another concept that we'll test in this experiment is Hess's law. You might have learned about Hess's law in your lecture, where if you don't know the delta H of a certain reaction, you can simply sum up the equations for reactions that you do know delta H for, and also sum up their delta H's. This is represented in the following equation. If we need to find delta H for reaction number 4, we can sum up the delta H's for reactions 1, 2, and 3 along with the reactions to obtain delta H for reaction 4. We'll be testing this by comparing runs 3 and 4 with run number 1 to see if there is a Hess's law type relationship. In part 3 of this experiment, we'll be doing a calorimetric calculation where we calculate the delta H for the reaction between a strong acid and a strong base. To do this calculation, we first need to calculate Q for our surroundings. In this case, the surroundings is all of the water plus the calorimeter in which the reaction is taking place. We can calculate this if we know the total mass of our solution, which will be about 60 grams. The specific heat of the solution, which is given in your lab, and delta T, which we'll be measuring. We then use this first law of thermodynamics to figure out the delta H. We notice that from the first law that Q for the system plus Q for the surroundings must equal 0 for energy to be conserved. This implies that Q for your reaction must equal minus Q for your surroundings. And we also know that Q for a reaction will be about equal to delta H for that reaction. You'll compare this value with a value calculated by standard enthalpies of formation. Here are some specific points about the procedure we're using. Just like in experiment number 8, we'll be using a coffee cup calorimeter where 2 styrofoam cups are nested together. The calorimeter will then be stabilized by placing it in a 400 milliliter beaker. The vernier temperature sensor will then be stuck through the hole in the lid, which will be placed on top of the calorimeter. We will then use LoggerPro software to carry out our experiment. This time, however, we're going to use a new type of data collection called Events with Entry. Events with Entry allow you to record, in this case, a temperature for a specific event or measurement. There are 2 types of events that we'll be using. In part 1, we simply want to know the temperature at the beginning and end of our reaction. This means that we will enter a text label for each measurement. In part 2, we would like to create a graph of heat versus, or temperature versus the volume of space added. In this case, we want to enter a numerical label, milliliters of base added, so that we can create our graph. These 2 types of data entry will be outlined in the lab video. Finally, normally when we do this experiment in person, we pull all class data, in which all 12 groups in the lab, assuming 24 students, carry out the different runs in part 1, and then we calculate an average and the standard deviation of the mean. We're not able to do this in a lab video, at least not in a live setting. However, we will simulate this by providing you with some class data. It is important to use that class data and the averages and standard deviations of the mean that you calculate to do your comparisons. Remember, when you use an average and the standard deviation of the mean, that standard deviation of the mean creates a range in which your measured average can be with uncertainty. If you compare 2 temperatures, average temperatures, and your ranges do not overlap, you can conclude that those 2 averages are significantly different. If the ranges do overlap, then you can assume that those temperatures are about the same within standard error.